What if the very tools we built to solve our hardest problems are secretly limited by the language we use to describe them? Imagine a world where artificial intelligence can reason through ultra-long contexts with near-perfect accuracy, yet still stumble over the basic task of understanding its own output. This paradox sits at the heart of today's most groundbreaking research in machine learning. Welcome to a deep dive into the intelligence revolution of 2026. Today, we are unpacking a series of startling discoveries that challenge how we build, train, and trust our AI systems. We will explore why standard methods are hitting invisible walls, how new optimizers are reshaping the landscape of deep learning, and what these findings mean for the future of human-AI collaboration. Stay until the end because the final revelation about the limits of language itself might just change how you view every conversation you've ever had with a machine. For years, the field of artificial intelligence has operated under a powerful assumption that with enough data and enough computing power, we could create universal problem solvers. We believed that if we just scaled our models up to billions of parameters, they would naturally learn to generalize across any domain, from solving complex mathematical puzzles to diagnosing medical conditions. However, a growing body of rigorous research suggests that this belief is only partially true. While we have made leaps in processing speed and pattern recognition, we are encountering fundamental obstructions that prevent true universality. The problem isn't just a lack of data or computing power. It is a structural mismatch between the way machines learn and the way reality, particularly human language, is structured. When we push these systems to their limits, asking them to reason through sequences of 128,000 tokens or navigate heavy-tailed noise in massive datasets, the cracks begin to show. So, what have researchers actually found? The discoveries coming out this month are nothing short of transformative. First, let's talk about length generalization. A new approach called randomized RN has shattered previous records, achieving over 90% accuracy on benchmarks for sequences far exceeding what models were trained on. By combining randomized positional encoding with a curriculum that exposes models to out-of-distribution positions during training, scientists have moved the field from mere extension of known data to genuine generalization. This means AI can now robustly reason through ultra-long contexts without needing to be retrained for every new scenario. But the story gets even more interesting when we look at the engines driving these models. For a long time, AdamW has been the default optimizer for deep learning. Yet, new theoretical work reveals that under the heavy-tailed noise common in large-scale pre-training, AdamW actually fails to match the sharp convergence rates of newer, sign-based optimizers like Lion and Muon. It turns out that AdamW's reliance on second-moment accumulators creates a theoretical obstruction, effectively hitting a ceiling that these newer methods bypass with ease. This is a paradigm shift, challenging the default settings we've used for years and suggesting that the geometry of our optimization landscape requires a different kind of navigation. Furthermore, we are seeing a move toward dynamic tool invocation. The newly proposed AIR framework empowers multimodal models to autonomously invoke Python code during complex reasoning tasks. Instead of statically manipulating data, these systems now act like human problem solvers, triggering external calculators only when mental calculation becomes insufficient. This has led to a nearly 10 percentage point increase in performance for interleaved reasoning samples, mirroring the way humans reach for a calculator when a mental math problem gets too tough. Perhaps most profoundly, researchers have finally proven mathematically that prompt-conditioned language models are not universal problem solvers. The issue lies in natural language itself. Language acts as a capacity-limited communication channel, creating an irreducible error floor. When we try to map continuous concepts, like pain severity, to discrete scales, we create an aliasing effect that no amount of scaling can resolve. This means that while we can reduce estimation errors by gathering more data, we cannot eliminate the structural ambiguity inherent in text-based interfaces. Additionally, studies on self-reporting reveal a startling gap. Current models largely fail to reliably recognize their own outputs when generated via adversarial profils. While some techniques can collapse this gap, others intended to improve introspection have ironically increased the success rate of attacks, warning us that alignment methods must be handled with extreme precision. These findings ripple far beyond the laboratory, reshaping our understanding of intelligence and our relationship with technology. The realization that AI is not a magic bullet for all logical deduction forces us to rethink our expectations. We are moving away from the dream of a single, all-knowing oracle and toward a future of specialized, collaborative agents. The discovery that optimization dynamics depend heavily on the geometry of the problem space means that one-size-fits-all algorithms are becoming obsolete. We must now design systems that are sensitive to the specific topology of the tasks they face, whether that is the angular step size decay in billion-parameter models or the communication protocols in multi-agent workflows. Moreover, the disconnect between static policy metrics and the dynamic reality of AI exposure highlights a critical failure in our ecosystem. With 80% of the workforce now facing tasks exposed to large language models, relying on outdated static scores is no enough. We need dynamic metrics that evolve with the technology.